rivals prior to graduation.
Also every lunch that's
Well, tomorrow I'm going to drive.
10% owned by NVIDIA. We'll see.
All right, Kunal, Agrawal's going to give her next spot, and it'll be on managing high bandwidth memory.
Right, thank you, Kirk. So even though I've done a little bit work on high bandwidth memory, I actually learned more about high bandwidth memory during boot camp and yesterday than I ever knew before. I'm a theoretician, so this is going to be a theory talk. But at a high level, the things, and there's probably something that's not true here, but at a high level, high bandwidth memory is memory technology that is being used on GPUs right now. And it may be used on CPUs in the future. And it has high bandwidth. That's sort of all we currently care about for the purposes of this talk. And just to sort of at a very abstract level, what are the properties of high bandwidth memory? Just qualitatively, right? So let's look at DRAM and cache. So there are 3 dimensions. There's latency, bandwidth, and memory capacity. So DRAM has really high memory capacity, which is good. But it has high latency and low bandwidth, which is bad. And we like caches. In our memory hierarchy, there are caches which have low latency, they have high bandwidth, but they're small, right? And high bandwidth memory has high latency still. It uses the same technology as DRAM. And we heard other reasons that it still has high latency. It has high bandwidth. That's its main advantage. And it can be large, so it's larger than caches, but generally not quite as large as DRAM. Okay, so it's still limited capacity. So so it's not like cache or DRAM, and generally explicitly managed by software. So caches are generally managed directly by hardware. HBMs are normally explicitly managed by software. And the question is, how should we manage it? Okay. So we're going to ask this question from a theoretical perspective. So let's first model HBMs. Like, how do we want to think about HBMs? So here's the HBM. So there are processors, there's HBM, and there's DRAM. And DRAM or memory, this holds all your data. And HBM has K pages. So it has high bandwidth, right? So the way we're going to model high bandwidth is that you have processors, and you have lots of channels from the processors to the memory. It has low bandwidth. So DRAM has limited bandwidth. So to transfer stuff from DRAM to HBM, there's only one channel. Okay? Both have approximately the same latency, so we're going to assume that the latency on these channels and the latency on these channels is 1. And there's limited capacity. So HBM has K pages. It can only hold K pages. So this looks familiar if you've worked on caches on the external memory model. Can I just think of this as a cache? Right? So one of the most successful theoretical models that people have designed is the external memory model. And this models caching, right? Or fast memory, slow memory, the memory hierarchy. So generally, you have a small memory, which is cache. Sometimes this also models DRAM to disk. But regardless, there are 2 types of memory. There's the fast memory, which is cache. There's slow memory. In this case, it's DRAM. And what we want to minimize in this model is the number of transfers from DRAM to cache, right? This is the external memory model. Okay? And the nice thing is it's a hammer, right? Like there's decades of work on designing strategies to manage the cache. And there's cache-efficient algorithms and data structures, such as B trees. We know a lot about caching, right? So is this a hammer we can just use for HBM as well? And I'm going to make a few different arguments to say why it's not. Like, why can't we just use whatever we know about caches to apply to HBM directly? So I'm going to start with my first argument. So one of the important properties of the external memory model is that we want to minimize the number of page transfers between DRAM and cache. Okay? And why do we want to do this? Like, we don't actually care about page transfers, right? What we care about is the running time. But for caches, the number of page transfers is generally a good proxy for running time. So you can separately minimize the number of page transfers, and then you can separately minimize something else, and you combine it all together, you get good running time as well. This is not absolutely true all the time, but it's sort of true to the first approximation. Okay? For HBMs, this is really not true. Okay? So for HBM, a policy that minimizes the number of page transfers can be up to omega p worse than the optimal for running time. Okay? So you can design a policy that is very, very, very good for minimizing the number of page transfers, but very, very, very bad for running time. All right? So that sort of kills this as our optimization criterion. Right? And very bad in the sense that it's optimally bad, right? You've lost all the advantage that you were going to get from bandwidth. Okay, so why is that? Just sort of intuitively. So HBM actually has two knobs. It has two scarce resources. That's the number of pages, right? Just like cache, it has limited capacity, but it also has this bandwidth. That's also a scarce resource that you have to manage. So what you need to design are two policies in some sense. You want a page replacement policy, which says what K pages do I want to keep in HBM at any time. This is what you do for caches. But you also need to decide how to use this channel. If lots of pages need to be transferred from DRAM to HBM, what page should you transfer first? Okay? So an HBM management strategy needs to design both a page replacement algorithm and a far channel arbitration policy. Okay? So let's look at a simplest problem we can imagine for HBM management. Let's say that you have these P channels, right? So you have P threads that are accessing these channels. And think of these as processes if you want to. They're all accessing disjoint pages. So there are no shared pages between threads. Okay, so every thread sort of has its own channel. Okay, and we want to minimize something, right? So we want to minimize some metric of the completion time of these threads. So for instance, we want to minimize make span or sum of completion. You can imagine many metrics, right? So again, we're going to, for now, for the next couple of slides, let's consider the simplest possible metric, which is the make span. You just want to finish all the work, right? Yeah. So now let's try to design a policy, right? So we want to design a page replacement policy. And we know for caches, LRU is good, right? So let's say we'll just use LRU. Okay. And what about the far channel arbitration? So if multiple requests are waiting on this channel, right? Everybody requests a page. None of the pages are in the HBM. You want to get a page. What do? Well, let's do something fair, right? First come, first serve. Whoever requested a page first gets the page first. Okay? So this is a policy you could imagine, and we did. And we were like, oh, this policy must be good, right? Like, what could possibly go wrong? Well, this policy is maximally bad. Okay, so this is as bad as it can possibly be. Again, you get no benefit from having an HBM at all. You may as well remove it, and you'd be fine. In fact, you might be a little bit better. You lose a constant factor just by going through HBM. Okay, so why is that? Why is this policy so bad? The thing is, HBM management is a little bit weird. Okay, and the reason it's weird is that page transfers take different amounts of time based on other page transfers that are happening. So imagine that all of these threads start executing. HBM doesn't have any of their pages, so they all start waiting on getting the page, right? So the first page takes unit time to transfer, right? And then that thread sort of gets the first page, so maybe it queues up the next request. And then the next page takes 2 units of time to transfer, and so on. And this last page took p units of time to transfer, right? And then this page will, the second page of the first thread also now waits for p units of time. So this first come, first serve policy can essentially make everyone wait for a long time. Yeah. So the thing we did in our first paper is we designed a policy, which we called priority, that is order 1 competitive for make span. Okay, so it's possible to design good policies, but it's a very strange policy. It sort of arbitrarily prioritizes threads and tries to get threads done one at a time, essentially. Okay. One thing I should mention, here's another piece of evidence that says that HBMs are not like caches. Right? Because in caches, you almost always, there are no constant competitive deterministic algorithms without resource augmentation. And here's one for HBMs, right? So in that sense, it's a simpler problem than caches, in that you can design good algorithms without resource augmentation, at least for some problems, right? So it's a different type of problem, is all I'm saying. But now, what about other objectives, right? We said make span, okay, we can design a policy, but then, that's not the objective you want. You want mean completion time. And do we design a policy from scratch, right? We don't have sort of this thing which says, oh, minimize the number of page transfers, that'll make you happy. You have to sort of look at every objective one at a time, yeah? So what we figured out that HBM management doesn't seem to be like cache management, which is sad because cache management was a hammer, right? Maybe we could have used it. But like we're lazy, right? We'd like a hammer, right? So one would hope that like, okay, cache management is not the correct hammer. Maybe there's a different hammer that we already have. Okay. Yeah.
Sorry, can we go back to if you just pick an order of, so there's no locality between the threads because they're accessing different things, but
Yes.
the locality within the thread. So
Yes.
you just pick an order of the threads, then doesn't each of the traces of a single thread suffer the cache LRU problem, log N, log P?
Well, note that this is the same speed as this, right? So HBM, so the problem with caches is that this is cost 1 and this is cost 0 in the external memory model,
I see.
right? So all of the advantage of HBMs is because of these extra channels. So if you do threads one at a time, right, you're only getting one of these channels. Does that make sense? So the advantage is not because of latency. In caches, the advantage is because of latency. This is cost, in the external memory model, this is cost 1, this is cost 0, right? And this is fundamentally different.
Okay.
Yes?
Maybe extending on this, can I assume locality, like that most of the requests can be satisfied by the HBM, and then it's more seldom that I will get requests going to the DRAM, and maybe it will work. Okay. Or you're looking at the worst case?
We're looking at the worst case, yeah. We're doing like standard competitive analysis. Anything else? All right. So we're looking for a hammer. Okay? So we have this problem. We want a hammer, right? So what do we want from a hammer? Well, we have this HBM management problem, right? This is the problem we really want to solve. We want to solve the page replacement policy and the far channel arbitration policy. And the hammer we're going to use is actually a parallel job scheduling problem, right? Which, like, at first blush is not like related, right? But the advantage of this problem is just like caching. People have worked on these problems a lot. There are lots of models, there are lots of algorithms for lots of criteria, right? So if we wanted to do mean completion time, well, hundreds of papers looking at mean completion time. You want to do throughput, well, maybe not hundreds, but still probably a lot of papers looking at throughput, right? So lots of work, right? So can we apply these insights? So what we'd like is we've learned a bunch of stuff here. Can we just use that stuff without like spending a lot of time purposely designing these things? And hopefully we want to do this in some reasonable model that we already know something about or can easily find something about. Okay? So that's what we'd like. So what we did was that we almost got there, but not quite. So we had to define a new model, which was called the semi-normal model. This is not a model that people have looked at or studied a lot, but it looks a lot like normal models. Okay, so it's a familiar looking model, but not exactly like any of the models that we know about. But the good thing is that there's a black box conversion for algorithms in this model to algorithms for HBM. So in particular, if you figured out an alpha competitive algorithm in this model, then you get an alpha competitive algorithm for HBM in a black box conversion. And just to argue that this model is weird but not too weird, we show that a standard algorithm for mean completion time, which is round robin is good for mean completion time, is also good in this model. right? So even though we don't already have algorithms and analyses in this model, it's very likely that the algorithms in other models will end up working in this model as well, okay? So this is not 100% satisfying, but it's somewhat satisfying, okay? So now I think I've said like 90% of what I wanted to say. So now I'm just going to do some technical stuff. So feel free to ask me questions anytime, and I'll just do like just a high level sort of intuition of what this model is and why it works for HBMs. So what is this semi-normal model? So it's a parallel job scheduling model. So now I need you to forget everything about pages and memory and all that stuff, like blank slate, right? Like totally blank slate for now, right? So now we don't have any memory. We don't have any sort of threads or pages or any of that. We have machines. We have M machines and P jobs, okay? So you have 4 jobs here, and I have 12 machines. This is a processor with, this is a system with M machines which are identical, okay? And what does a job look like? And this is the semi-normal model jobs. Jobs are is a series of chunks, okay? So the first job has chunk 1, chunk 2, chunk 3, chunk 4. And these chunks have sizes. So the first chunk of job 1 is 3, the second chunk is 5, the third chunk is 2, the next chunk is 5, and so on. They can be any size, okay? Hopefully less than 12. And the same thing for all the other jobs, okay? And you can think of this chunk, the width of this chunk, as the job's demand of processors for processing this chunk. So the first job needs 3 processors to process its first chunk, okay? And on time step T, some scheduler just decides how many processors each job gets. However it does it, I don't know. Somehow it decides the job's allocation. So the job 1 got 3 chunks, job 2 got 1 chunk, job 3 also got 3 chunks, job 4 got 2 chunks. Somehow this was decided, okay? And a job is able to execute its chunk if the number of processors it had was more than the size of the chunk. So in this case, all the jobs are able to make progress on their chunks because they had sufficient number of processors, okay? Let's do another one. Now, in this one, again, job 1 got 5 chunks, job 2 got 3 chunks, job 3 only got 3 processors, job 3 only got 2 processors, and job 4 got 2 processors. And now, job 3 cannot make progress. It's stuck. Unless it gets the sufficient number of processors, it makes no progress on the chunk. So it's not that it makes partial progress on the chunk. It either has to execute the whole chunk or it does not. And a job completes when its last chunk is executed, okay? So that's what the model is. And a scheduling algorithm simply has to decide how many processors to give each job on every time step. The scheduling algorithm can be online or offline. It can may or may not know the width of the chunks, right? It could be oblivious or not. And it may optimize whatever metric you want, okay? So it's sort of a standard scheduling algorithm for this problem. And now why do I call it the semi-normal model? Well, there are many, many models, yes?
The equation you had a second ago.
Oh, sorry. This is just saying that the scheduling algorithm
the sum
can...
is less than M?
The number of M. This should be M.
Okay.
All right, one typo found. Sorry, it should be M.
Okay, just want to make sure. I was
Yes, sorry, yeah, it should be M. Okay, so there are many, many models for parallel jobs that people have studied. The semi-normal model kind of, if you squint, looks like many of them, but it doesn't appear, as far as we know, to be identical to any of them yet. But many algorithms and insights seem likely to transfer over. That's the hope anyway. So why is this weird-looking scheduling model interesting at all? Why do we care? So let me talk just briefly about how the reduction works, right? So now let's forget about processors for a minute, go back to HBM, right? So we have an HBM with K pages. We have P threads, which are going to try to access this HBM. And instead of like sort of doing something normal, what we're going to do is we're going to say, well, let's divide the HBM into chunks. So I let these accesses into chunks. So the first of K over 4 accesses. So I look at the first K over 4 accesses, and that's a chunk. The next K over 4 accesses is the next chunk, and so on. So those are the chunks. For all threads, we can imagine these chunks. And the working set of a chunk is the number of unique pages accessed within that chunk. So the working set might be different, right? In this chunk, this thread accesses the same pages over and over again, so its working set is small. This working set is large because maybe it accesses many different pages. So there are various working sets for each chunk. And then if a thread gets a certain amount of space on the HBM, what we know is that if the amount of space it got was bigger than the working set, then it can finish the whole chunk. Now, if it's smaller than the working set, it might still make progress. But we don't know how much. So pessimistically, we can sort of say maybe it made no progress or very, very little progress. So if we assume that it doesn't make any progress, then the sorry. This is similar to semi-normal jobs when a sufficient number of processors lets you make progress. In this case, sufficient number of pages let you make progress. So how does the result work? Well, we first show that if you give me an optimal HBM management algorithm, whatever that might be, you do what you want to do. You've designed a page replacement and a far channel arbitration policy. You can convert it into a chunked algorithm, and you don't lose too much. So the best chunked algorithm will be constant competitive with the arbitrary HBM management algorithm. Then we say, well, let's go to the semi-normal scheduling area. And let's say that you had an optimal semi-normal scheduler, right? What we want to design is an online scheduler A, which is alpha competitive for your objective, right? So this is the scheduling problem we would have to solve, right? We don't want to solve the HBM management problem. We want to solve the scheduling problem instead. So this is the scheduling problem we would solve. This is already done, so you don't have to do it again. And this would automatically give you an HBM algorithm in a black box conversion. So if you had a scheduling algorithm A, it would give you an HBM algorithm, which is alpha competitive with the optimal chunked algorithm. So you lost alpha here, you didn't lose anything here, so it's a order alpha competitive with the optimal. Right? So this I'm not showing you, but as a consequence, there's a natural round-robin scheduler, for instance, for mean completion time. And in the semi-normal model, it's order 1 competitive, which automatically gives you an order 1 competitive algorithm for mean completion time for HBMs. Yes?
In the diagram on the previous slide, you kind of, the intuition seemed to focus on allocation of space in the HBM and not, you didn't talk about allocating the channel, which seemed to be the bottleneck earlier. So I'm kind of, can you give me some?
Yeah, so because if you allocate space, so yes, I agree. The problem is that if you allocate space intelligently, then what you can do is you can say, well, spend a little bit of time just bringing in all that space into HBM, and then you're going to use that space properly. The problem with round robin is that you bring in something and then you hang out for a long time, and then you bring in something else and then you hang out for a long time, and so on, right? While this is sort of automatically designing both of them. So I didn't give you the intuition for that, but yes, the idea is that just like in cache, you can spend a little bit of time just warming up the cache, right? If you're smart enough about it, you can do that the same thing for HBMs. Yes?
For the vertical line going from the HBM algorithm to the chunk, Are you fixing chunk sizes, or is that part of the output?
The chunk sizes depend on your request sequences. So the request, just look at like the next k over 4 is just whatever, right?
You're
But
fixing the width.
no, I'm not fixing the width. I'm fixing the length, the number of accesses in the chunk, right? So
Yeah.
you're fixing this, right? But the width is the working set. That is not fixed,
You're
yes.
fixing the k by 4.
Yeah, I'm fixing the k by 4. But that's sort of a analysis red herring, right? It doesn't,
Oh,
yeah.
it is. Sure.
Any other questions? Right, so that's basically it. There are several open problems. So HPM management seems to reduce to a pretty natural scheduling problem. At least for this simple problem of threads with disjoint accesses, right? Maybe there are but this is a very simple problem, right? So if there are more complicated problems for HPM management, do insights from parallel job scheduling still apply, or is there a different hammer that applies? That's one question. The other question is we have this conversion from this weird model to HPM. If we could convert from a normal model to the semi-normal model, then we would have a conversion from a normal model to HPM. And it's not clear that this is not doable. The semi-normal model is a little bit weird. We weren't able to do it, but but this is probably possible. And this is one that I'm really interested in. All of the work so far, theory on HPMs, assumes this sort of disjoint thread accesses, right? But what we would like is to say, well, I'm running a parallel program. These threads share memory. What happens in that case? In the completely general case, it seems impossible to do anything. But if you have some constraint on the sort of what the accesses look like, maybe there's something to be done. I'm very interested in thinking about it. So if you're interested, come talk to me. Thank you. Yes.
So basically, just to understand if I got it right, the assumption for disjoint accesses when you want to prove that there is this correspondence between the two problems. Otherwise, in the HBM management, you would bring a page in and the others could use it, although it is right.
Yeah.
It is, and okay. I see. Thank you. Yeah.
So probably didn't hear it over the
Oh, yeah.
recording,
So the question, if I understood right, the question is that the problem with not using this reduction, but the problem with LRU plus round robin or FCSFS is that you clobber on each other's pages, right? And that's this is mitigating that problem to some extent, this conversion. Yes.
So the model looks a little bit like a shared cache, where you have P processes accessing a shared cache.
Yes.
So in what ways does it differ from that?
So for shared there are several ways, but let me just say for shared caches, even for disjoint accesses, there's a log P lower bound, even with resource augmentation for make span. While for this one, for make span, you can get order 1 competitive without resource augmentation. So it's just fundamentally different. And the difference is that the latency is not smaller, right? The latency to access HBM is the same as the latency to access DRAM. So the only advantage you have is in bandwidth. While caches, you have the latency advantage, which is much more powerful. So it's much more important that you use caches very well, and therefore optimal can sort of clobber you. It's not quite right, but sort of, right? So it's a fundamentally, the caching lower bounds just don't apply. Yeah.
So let's understand the model again. In the best possible way, if you use HBM in the best possible way, does it give only a order P?
Yes,
speed up?
the best. That's the best you can do. Yeah, that you have order P extra bandwidth. That's the best you can do. Yes. Yes.
Continuing the line of naive questions about how does this relate to parallel caching? So you have a universal construction for a competitive algorithm for parallel cache management, right?
For caching or
The green
for,
paging and the parallel?
Yes.
Yeah. if you just like take that thing and apply
So
it
that
here,
is
what happens?
order log P competitive.
Uh-huh.
There's a lower bound. No, I mean, in this, no, you wouldn't, so that one will not work here.
Okay.
Because I mean, one, it would be no better than log P competitive, because that one is specifically designed to be log P competitive. But I don't even know that it would be log P competitive. I haven't thought about it, but it would be no better than log P competitive.
Because it was also very job scheduling kind of like.
Yes, that also is sort of, parallel paging also turns into sort of like a job scheduling problem, but it still has some sort of, sequential paging is really not a job scheduling problem. Parallel paging, just like HBMs, is also sort of like a job scheduling problem. But this is like really a job scheduling problem. There's not a universal reduction from job scheduling to parallel paging, for instance. Like you're sort of using it a little bit, but you're not, the lower bounds don't apply back and forth and so on. Yeah. Yeah.
Is there an implicit assumption that K is greater than P?
Yes. There is sort of an implicit assumption that K is greater than P. There's a couple of other sort of implicit assumptions. If K is not bigger than P, then there's no point in having those many channels, right? At least in the disjoint access case.
The disjoint case.
Because why would you even do that, right?
I mean, I was sort of wondering why P didn't show up in the K/4 chunks. And nothing involved P, but I think it's because the assumption on P is buried in the assumption on K.
Yes, K is bigger than P. That is an assumption. Yes.
But where do you need this assumption in your proofs?
Sorry?
Where do you need this assumption in your proofs?
So if K was not bigger than P, then I think we would have to think about P at least a little bit in designing the chunks. I haven't thought too much about it, but I suspect that, I mean, if K is smaller than K smaller than P sort of just does not make sense in the disjoint access model, right? Because if I have P channels, right, I can only act, if I don't have more than P pages in my HBM, then I can't access P pages, right? So there's no real, like you may as well assume that you only have K channels.
But in your model, some threads may have to wait. So if K is smaller than P, again, you will have to choose which threads to serve, and some others will have to wait. And
if K were smaller,
maybe the problem is more difficult, but I don't see why exactly it wouldn't work.
It may work. I'm not
right?
confident. I suspect that this algorithm would also apply in that case. I'm not 100% confident, so I'd have to think about it.
Okay, thank
Yeah.
you.
Yes.
And then even naive questions. What about in the offline setting? So if you know the page request, is it easy or is it still NP hard?
It is NP hard. Both the make span is NP hard, mean completion, like it's all NP hard.
Thanks. Big again.